As everything in the world are made up of chemicals, there's too many of them. That is why organic and inorganic continue to be used in classifying compounds. And today we will slowly understand them one by one. Compounds can be identified and classified as to inorganic compounds or organic compounds. Each type of compound has their own characteristic, properties, and distinct chemicals or structural formula to represent the type of atoms or elements present. And nearly all compounds found in living organisms are still classified as organic compounds. Inorganic compounds are obtained from mineral from earth, like the salt, water, calcium, magnesium, so on and so forth. Organic compounds, on the other hand, are obtained from living organisms. So it is not only can be taken out from a human body or an animal body, but also it can be obtained from plants, the starch, the branches, or even the carbon we get from burning them. Organic compounds also include natural gas, petroleum, coal, gasoline, and many synthetic materials such as dye, plastic, and clothing fibers. To further understand the difference between organic and inorganic compounds, we will discuss them based on solubility, chemical formula, and the others. Solubility is the ability of solute to dissolve in solvent. As a review, solute is the one that is needed to dissolve, and it can be dissolved through the use of solvent or the one who will dissolve the solute. In solubility, if the solute is solid and solvent is liquid, we call this mixture soluble or insoluble. Soluble if the solute will be totally dissolved, and insoluble if solute will not be dissolved to solvent. There are also some mixture in which the solute is liquid and the solvent is liquid. The mixture therefore will be called as miscible or immiscible. Miscible if the solute will be totally dissolved by solvent, and immiscible if otherwise. Another thing that we will focus to differentiate them is based on the chemical formula. Chemical formula is a way of presenting information about the chemical proportions of atoms that constitute a particular chemical compound or molecule, using chemical element symbols, numbers, and sometimes also other symbols such as parentheses, dashes, brackets, commas, and plus and minus signs. Compounds could either be having hydrocarbons, which we consider as organic compounds, and if the compound doesn't have a hydrocarbon, we consider it as inorganic compound. Aside from these two properties, some also may be used to differentiate the two compounds. They could either be flammability, melting and boiling point, bonding, reaction, structure, so on and so forth. Since these properties has a vast topic and we may not finish it until tomorrow if we will include it in our discussion today, so this topic will be discussed on the lecture. For now, let's focus only on the two properties, which is the solubility and the chemical formula. First is solubility. In the experiment, we have two glasses with equal amount of water. On the first glass, we added a salt, while on the other glass, we added oil. Note that the salt and oil in the experiment is the solute, while the water is the solvent. The salt in water was dissolved as observed, while the oil in water was not. So what learning can we get out from this experiment? The solubility has very simple theory. Remember the phrase, like dissolves like. Let's take a look on the chemical formula of our ingredients. First is the solvent, which is water. Water has a chemical formula, 2 hydrogen and oxygen, or we simply read it as dihydrogen oxide, or more commonly read as H2O. We know for sure that water is an inorganic compound because it doesn't have any hydrocarbon. Like dissolves like, so water will dissolve inorganic compounds also and not organic compounds. In our setup, the first glass you notice upon mixing the salt or with the chemical formula sodium chloride, the salt which is solid dissolves in water. Therefore, salt is an inorganic compound since it was dissolved in the water which is an inorganic compound. An oil, on the other hand, which is a liquid, was not dissolved in water. Therefore, oil is an example of organic compound. And to have a proper way of describing their solubility, we will use soluble for the dissolved salt and immiscible for the undissolved liquid oil. Organic compounds are the chemical basis for life itself. As many mayayaman would choose, almost everything should be organic. And almost all we consume are made up of organic compounds. The proteins, carbohydrates, enzymes, and hormones all are made up of organic molecules. Based on the chemical formula, one thing we need to look for to differentiate the compounds is the presence or absence of hydrocarbon. Let's focus on hydrocarbons which the organic compounds has. Also for today, since our subject is pharmaceutical organic chemistry, let's focus more on organic compounds only and not on inorganic compounds. Hydrocarbons, from its name implies, are a combination of hydro or hydrogen and carbon only. Therefore, organic compounds not only should focus on carbon but rather of these two elements, hydrogen and carbon. It is also our hint in classifying whether the compound is an organic or inorganic. There are compounds that has carbon in them, but cannot be considered as organic. Example, the compound carbon dioxide is considered as inorganic. Yes, living organisms produce it, but so do many other natural processes. Thus, it has classified as inorganic. Other are like sodium bicarbonate. It may have carbon in them, but they are considered inorganic. So to really consider as organic, the compound or the molecule should compose of hydrogen and carbon. For an introduction to the organic chemistry, let's have a brief overview of the functional groups in organic compounds. Let's proceed now with the first functional group, alkane. Alkane is the simplest hydrocarbon that consists of four covalent bonds. Covalent bond, which is the line in here. So again, alkane consists of four covalent bonds bonded with hydrogen. You have to remember that alkane is a single bond and has a general formula RH. But what is R in the general formula RH? R, or other called it R group, is any group in which carbon, hydrogen, or hydrocarbon is attached to the rest of the molecules. In naming your alkane, the prefix will constitute to the number of carbons followed by the suffix A and E. Example, we have here the simplest alkane, methane. There is only one carbon. It is taken from the suffix meth or one. So, meth plus the suffix A and E, we have the name methane. Alkene, the E and E ending, are the hydrocarbons that contain double covalent bond between two carbon atoms. One thing to note, just like the alkanes, each carbon atoms needs four covalent bond. Thus, the simplest alkane is ethane, as the single carbon atom, which is methane, cannot produce a double bond on hydrogen and only on carbon. Therefore, for alkene, you need to have two carbon for them to have the double bond. Ethane molecule is completed with two hydrogen atoms in both of their carbons to complete the four bonds. Next is the alkyne, or the hydrocarbons with triple bonds. We got here the ending Y and E with the general formula RC triple bonds CR. The simplest alkyne is ethyne. Similarly with alkene, we cannot have the triple bond on one carbon only. Therefore, our simplest hydrocarbon for alkyne is ethyne. Next, we will proceed from simple hydrocarbons to organic molecules, which was grouped because of their similar structure and properties. First is the alkyl halides, or hydrocarbons bonded to a halogen. What is halogen? Halogen can be found in column 7 of your periodic table. They are fluorine, fluorine, bromine, and iodine. To name them, you simply count the carbon, then the ending of halogen changing to O. Example, the structure that we have here. Hydrocarbon, as you can see, our hydrocarbon here has 2 carbon. And it has a halogen which is the chlorine. Therefore, we need to change the ending of chlorine INE to O, making it as chloro, plus the hydrocarbon which is the 2 or which is having 2 carbon. Therefore, the name now of our alkyl halide is chloroethane. From halogen, we will now proceed with those having oxygen in their structure. First is the alcohol. It is a hydroxyl group where hydrogen is bonded to an oxygen, which is also covalently bonded with the rest of the group. Again, hydroxyl meaning there is a oxygen bonded with hydrogen. That is why the general formula is ROH. Important note to remember the hydroxyl group for alcohol, or the OH. An alcohol group can be attached from any of the alkane or hydrocarbons. How will you name this? First, count the number of carbon, and since it is an alcohol because of the hydroxyl, ending is alcohol or the suffix OL. Like for example, the simplest alcohol is methanol. In the structure you see here, we have 1 carbon, so this is a methane, plus the OH, meaning this is an alcohol. So methane, changing the ending A and E to OL, we now have the name methanol. So if the molecule has 2 carbon, that's considered now as ethanol. If 3, propanol, and if lahat ay gumagamit na ng alcohol dahil sa COVID prevention, we call it as sanaol. Another oxygen-containing group is ether. Ether has oxygen at the center of 2R group. In naming, we simply add in the ending ether. Example here, the simplest ether is dimethyl ether. Next is aldehyde. You might confuse it with alcohol. However, take note that aldehyde is a carbonyl group and alcohol is a hydroxyl group. Carbonyl group is the carbon bonded with double band oxygen. Just like in the example given, we have here a carbon plus the double band O. So this structure here is what we call carbonyl group. Remember also that the general formula of aldehyde is RCHO. In naming them, we simply add the word aldehyde or the suffix NAL or NAL. Example is the simplest aldehyde, methanol. Next we have here is ketone. One thing to take note is that it is the same with aldehyde in the sense that they have a carbonyl in their structure. However, since aldehyde has a formula RCHO, we always expect aldehyde to be found at first or last carbon, while on ketone, since it has a formula RCOR, meaning it can always be found at the center of the molecule. In naming, we simply add the ending O and E or 1. Example, the simplest ketone is propane, or the molecule having the 3-carbon atom. It will now become propanone, or commonly known as acetone, our nail polish remover. Next is carboxylic acid. If ketone and aldehyde has carbonyl group, carboxylic acid has its carboxyl group. Carboxyl group is a hydroxyl group with a carbon double-banded oxygen. Let's see in the example again. A carboxyl group is a hydroxyl group with C double-banded with oxygen. It's like an aldehyde, the C double band O, and added with alcohol or the hydroxyl group. Carboxylic acid have the formula RCOOH. In naming, we simply put the ending OIC plus the word acid. Example, the simplest carboxylic acid we have here is methanoic acid. Methanoic acid is more commonly known as formic acid, or this is the venom found on ants. This is the liquid that comes out in ants when you kill them and is responsible for the redness in the ant bites. There is a derivative of carboxylic acid, and that is ester. Ester is a carboxyl group derivative because instead of hydrogen on the hydroxyl part of carboxylic acid, ester derived it with R group. As you can see in our example here, since the carboxylic acid is a C double banded with O and with a OH or hydroxyl group here, the H was derived or changed into R group. Again, carboxyl group derivative ester is a C double band O, O, and another R group. Thus, ester simply has formula RCOOR. You always see ester on the center and thus it separates to carboxylic acid, in which you always see carboxylic acid on the first or last carbon similarly with aldehyde, while ester are similarly with ketone in which you see them on the center of the molecule. In naming, we simply have the ending OATE. Example, the simplest ester, methyl methanoate. Ester gives a molecule a sweet smell used for perfumes or flavoring. So the next time you smell a sweet odor from a perfume, it's definitely an ester. The next group we have are the group having nitrogen in their formula. First we have is amines or amine. Amine are organic compounds having an amino group or the NH2. It is attached somewhere in the carbon chain. They are used to dyes and for making medicine. Example, methamphetamines are commonly known as shabu. Methamphetamine actually is not bad at all. It has a medicinal usage. However, it is not used in the market because of high addiction it could give to the one using it. Methamphetamine is used to treat attention deficit hyperactivity disorder or commonly known as ADHD. Methamphetamine is also used to treat obesity in people who have not lost weight with diets or other treatments. In naming them, you simply add the ending amine. Example, the simplest amine or amine is methylamine. Last functional group we have is amide or those having a carboxamide. Again, those having carboxamide. Carboxamide is a carbon double bonded to oxygen with nitrogen in it. As you can see in our example here, we have the C double bond O plus the nitrogen group. It's separate to amines because amines has single bonded carbon while amide has double bonded carbon. In naming, we simply add the suffix amide. Example, the simplest amide we have is the ethanamide. Let's now have some exercise based on the functional groups we have discussed. You have to identify what is the functional group of the picture that will be shown. First picture, what is the functional group of formaldehyde? Let's have a clue. Formaldehyde is also known as methanol, a single hydrocarbon having a carbonyl group, and since it is a methanol, it has the ending nal. This is therefore aldehyde. Next example, ang hindi nawawala sa kusina. We have here the vinegar. Vinegar has a chemical name acetic acid or also known as ethanoic acid. Since the ending is OIC plus the word acid, therefore this is carboxylic acid. Next, the acetone. Acetone is also known as propanone. Propanone, as the name implies, with the ending ONE. Therefore, this is ketone. Last example we have is butane. This is the 4-carbon hydrocarbon. Very obvious, the answer is alkane. To summarize all of these functional groups, let's group them according to their structure. First, we have the pure hydrocarbons, the alkane, alkene, and alkyne. Next is those having halogen, we call them alkyl halide. We also have those hydrocarbon having oxygen in their structure, namely alcohol, ether, aldehyde, ketone, and carboxylic acid. Next, we have the carboxylic acid derivatives. We have the esters and amides. And lastly, having the nitrogen in their structure, which is amines. And that's it for this video. I hope you learned something out from this discussion. If you have any question from the lesson, don't hesitate to ask me. I'm only one chat away. Till next time, ciao!